The last video I was making cut out on me. So we're going to be doing lab number 7, where we're using an ohm meter to measure for resistance in a series circuit. That was what I had you guys doing last week. Select 5 resistors from the resistor bag. Each resistor should be rated between 100 and 10,000 ohms, so that we don't have some huge million ohm value that we're looking at here. I'm going to make it very straightforward. I'm going to use 5 100 ohm resistors as I'm going through this. So I started it up here before the video stopped on us, and I started putting these up here. So I'm just going to start at that point there. Really important when we're measuring resistance is that we acknowledge that we are not supplying any power to the circuit. So there's no power to what we're doing here. I have a resistor just laying on a piece of paper here, and I'm going to take my ohm meter and I'm going to bring that up to my resistor. So number 1 is 101, and that's what it says there. So this is our number 1 resistor. I'm going to set that over here on a board. Number 2, and this is brown, black, black. So this is a 10 ohm resistor, so I'm not going to use that one. The second one is brown, black, brown. Brown 1, black 0, brown 1. So 1, 0, and then 1, 0 afterwards. That third number tells us how many zeros or what power it goes to, the multiplier. Really just think of it as how many zeros follow that. So 1, 0, and then 1, 0 following. It's a 100 ohm resistor. And one last thing as a review as well. All of these resistors that I'm showing you here, they have a gold tolerance band. The gold tolerance band is 5%. So we're looking for resistors that are 105 to 95 ohms. That makes it inside of tolerance for what they'd be doing. The next one is going to be measuring at, let me pull my hand away so you can see the meter. Can you see the meter? No, now you can. 104 101 ohms. So it's a 100 ohm resistor and it's 101 ohms. I'll put that down here. 100 ohm resistor and 101. And I'll set that to be number 3. Because at some point here I'm going to find that 100.7 again. There's no polarity with resistance. Doesn't matter which side my negative and positive are on. 100.8. So we'll use this one here as number 2. And then these two. .4. It's a 100 ohm resistor. And we're getting 100.4. Does that mean anything, that 0.4 there in ohms? No, it's such a small amount. It doesn't really mean that much. I'm putting it on just to be as accurate as I can for you guys here. And number 5 resistor, we'll go ahead and check that one. 100.8. So the color code is a 100 ohm resistor and it's 100.8 ohms. Okay. So now what we want to do is we want to measure these in a series circuit. So a series circuit would, at its bare roots, would be if I twisted these two together, or if they touched each other right there, and I measured on the opposite ends, it should be going through and measuring the entire resistance of that wire right there. So another way of doing the exact same thing is using a breadboard. This is one example of a breadboard that I showed you in the room there. This is one that has dovetails on the side there, so connect to other boards to make a very large circuit. An electronics engineer who's trying to work out a circuit for whatever project they're working on would use one of these because it's solderless. So when we put this resistor R5 into this, pushes into the one side there, that one side there would be C12, and C12 would go to 40J if I put that at 40J. So we'd be able to do a circuit in this manner right here. This is a smaller one. The holes are smaller. It's more difficult to comprehend. This is a larger one of the exact same thing, mind you. So this has 5, 5, 5, 5. Each group of 5 has 2 springs, so that when I push into this, the springs are holding the end of that resistor in. If I went from here to here, meaning that they're in the same 5, and I measured that, it would not go through my resistor. So I should not be getting 100 ohms here, because it should be able just to go right down through the bottoms there. A lot of times these coils have been worked over a little bit, but you see we're getting 4.0 ohms on this. So it's not the 100 ohms that we just measured there. It's 4.0, because it should be taking the path down below the coil there, going through here. So my resistor going through a straight conductor, like the 2 ends of the wire here, shouldn't be measuring the resistance of that resistor. It should just be measuring the resistance of the wire. So the resistance of this wire right here is 2.6, which is the same as it was with just touching the 2 leads together. So if I were to set this one here and then bring the other end of this resistor into another group, then that should measure what the resistance of the resistor is, 100.3, right? So that if I take another one, so here it's saying wire R1 and R2 and take a resistance reading. So R1 was up here. I'm going to put that in and have those come across like that. And then R2, I can go into the same hole, or I can go next to it. It won't matter. Any of these holes here should be connected to that. R2, and bring that over to this lead. If I take those 2 together and measure that total resistance, I'm getting 202.5. So these are 2 100 ohm resistors. 202.5 sounds right. We found out last week that RT equals R1 plus R2 plus R3. So to get 200 with 2 100 ohm resistors makes total sense, right? And it should make total sense that we should be getting 300 with another 100 ohm resistor, and 400 with another ohm resistor, and finally 500 at the end here to demonstrate this. So now this comes over here. Remember, 1 leg's in the one group of 5, and then the 2 legs of the ones that are joining each other go to the next ones. So we have 1, 2, 2, 1. So if I go across all 3 of those, 304.1 ohms, 305.1. We are getting some resistance in these springs that are down below here, so it's not working out perfectly. I know in class it's frustrating for me and for you when the numbers don't work out just absolutely perfectly, but there are factors going into this that are beyond what we can control here. Now I did with my light board there, I sanded all the terminals, and I also gave them a little spray of an electronics cleaner here to try to keep all the connections clean. So I did not spray this board though, so that board is, any rust that's in any of those springs there is there. So if we take another one, 4th one, and go across all 4 of these now, said 0.4 kilo ohms. Okay, so that's 411 ohms for these. They changed it now from going from hundreds, now they're using kilo. And I'm not sure at what point this meter, this digital multimeter does that, but now we're at 0.4 kilo ohms. Okay? Go for the next one, out to the end. .53 kilo ohms, or 530 ohms. Okay, so looking back at this lab now, we added the 2 resistors, we got 200 ohms. They're both 100 ohm resistors. 3 resistors, 300 ohms, 400 ohms, 500 ohms. So correct what we did last week. RT equals R1 plus R2 plus R3, etc. Because that's going to keep. If I would have had a 200 ohm resistor in that series, 200 ohms would have been added to our total as we went along here. Okay. I want to do one more thing before we stop here. I want to show you how we'd set up this all going on here. So I'll put that one back in there. That goes my 10 ohms. So to kind of go through everything that we've done so far, and we're at 10 minutes right now. If I set this up, negative, comes in, goes across, goes across, goes across, comes over, goes across, comes here, and then needs to be returned back to my positive side of the power supply. Then I can switch my digital multimeter to voltage, direct current, and I can measure my power supply, my positive and my negative. I have 5.8 volts. Do you see the negative there? My polarity is reversed. Negative, positive, now to read correctly, 5.78 volts. I can go through each one of these and find out the individual voltage drops each one of these. 1.1, 1.6, 1.2. Remember, when I want to do the current now, I have to take that out, and I will hook up my negative to the negative side here, because voltage and current both require polarity to be correct. And I can figure out what my current is going to be. Amps, direct current. So you see my lights are on. My lights are on. I'm getting 207 milliamps, or 0.207 amps. And then if I want to do my resistance, the first thing I have to do is take the power off the power supply. I do not have any power to this right now. And I'm going to measure my resistance going down the line here. So I'll connect this again. And going across, remember there's no polarity here, so there's no negative and positive. Going across these two, go back to resistance. These two here, 20.6 ohms. That does not sound correct. Let's take a look at this. 20.6 ohms going across there. I'm not sure why that's reading such a high number here. Let's see if I come closer to them, if I'm still getting 20.6. I am. This bulb, however, if I hold it to here, I'll put it against the plastic, hold there and touch the bottom end, this bulb is 20.5 ohms. It seems like a very high resistance for this bulb here. If I take this bulb out and measure the resistance of that filament, $20.9. 20.9. Measure this one. $20.6. Something is going on here, which is, if you look at my two leads here, I'm getting 19.6 ohms of resistance with my leads. So something is going on with this. It's adding on to that, adding on to the resistance. Let's see if I turn it off, turn it back on again, if that corrects itself. $3.3. Okay, so something was going on with that, with the meter there. That's why I was getting such huge numbers. We wouldn't be getting 20 ohms with that small light bulb there. So I'm going to go back to the beginning here. 3.4 ohms. So that seems like a very high number here as well. So I'm looking at 30 ohms here going across. We know this is about a 3 ohm filament here. So to be getting this high number, oh, there we go, 5.9, 27, makes me wonder what's going on. So I'll test the bulb by itself. .6. So in this one here, my thought is that there's some kind of external resistance here, one of the wires or something. My meter is giving me, when I have it zeroed, at 2.3. So I'll bring this back up again. So 6.4, and then when I move it out to the outsides here, I'll be getting 5.5. That makes more sense. .7, 3.6. So if I want to get the total resistance, I have to put my resistance meters, my ohm meters, all the way across. So at one end and at the opposite end. We're getting a lot of fluctuation here, so I want to get it where I can be at a number that I feel is steadied. 9.6 ohms. Let's see if that makes sense. So here we have 3.2. So we're already at almost 9 there between those two. 3.6. 3.6 across those as well. What about through this conductor here? Conductor's 2.4. So now through all 4 bulbs again. 12.1, 10.7, 10.1. We should be getting, and I'm going to bring this up again so I can make sure that you guys do see that this is a fact. We have a voltage total of about 5.7 volts here, and we have 0.206 amps. RT equals, well, Ohm's law, if we did this mathematically, we have voltage, current, resistance. So if we know what VT is and IT is, that we can find RT. Now we have to keep those in mind, that each one of these is going to be the same here. So it's going to be like this, where it's going to be 5.7 over IT, which is 0.206. So if we take 5.7 and divide that by 0.206, we should theoretically get what the total resistance in here is. 27.67. 27. And very honestly, that's what I've gotten a lot when I'm sitting down here just going through this, making sure that it's going to come out the way I want, and it doesn't always come out that way. But more times than not, this has been what I've been measuring for a total resistance for this circuit. Why I'm not right now, why I'm getting less resistance, it doesn't always work out perfectly. I'll put that on again and just see if I get a number closer to our 27.67 here. .3 again. So what's the ohm meter doing? The ohm meter is sending out a small trickle amount of current, one that it knows what it's sending, a constant. And that's going through the circuit, and it's finding out how much resistance is to each of those. I just turned it off and on again and see if that's going to change this for us. We should be getting a number in the 20s. 9.1 ohms again, which does not make sense for what we're doing here. So, when we take that, and again, this value here was VT, this value here was IT, and we divide them, 5.7 divided by 0.206, we should get 2767, and that is going to be ohms, and that is going to be RT. Okay? If we wanted to break that down into smaller areas to find out what the resistance is in theory of different bulbs here, we would take how much the individual voltage drop of this was and the current of this was. So that would be, the current would be the exact same because IT is constant throughout here. My current here is the same as it is here, is the same as it is here, same as it is here. So that number would not change. The VT would change. So the number that I'm using in the numerator here for my division would change, and that would alter what we have here. And that would give us what the resistance of that individual area is. So let's do that. Let's take my voltmeter, and we have negative. Actually, I'll take my positive over here. This is positive. Positive goes there, and negative goes there. Okay? So this is the same circuit that we've been doing, so we can still use that number for current. IT equals 0.206. Okay? And I'll show you that again. So IT, I'm going to put it right in here. Measure for L1 here. I'll put it right in the very beginning. So I'll come from the negative to the negative side of my meter, and then the positive side of my meter in front of that. So this is in front of L1, so it's current of L1. So we're getting 208 milliamps. Okay? Another way of saying the same thing is 0.208 amps. 0.20, we'll use 8 because we just saw that, and that's amps. Okay? If we want to know what the voltage drop of L1 is, this is not IT, this is I1. And now we're going to find V1 equals, so I'll go to voltage. I will hook up my power supply again so that my lights are lit, and I'll find out what the voltage drop across this is. 1.23. 1.23. So we know what I of L1 equals 0.208, and I had to convert that to amps from milliamps. I cannot do this. I cannot use the Ohm's law formula using milliamps. I have to use full units for this. So now V of L1 equals 1.23 volts. Now what we want to do is find R1 on here. So mathematically, if we did this before we even tried it to see what it would come up with, it should be that I'm taking my voltage over my current. So it should be 1.23 divided by 0.208 equals 5.9. Let me do it again. 1.23 divided by 0.208 equals 5.9. So 5.9 ohms should be what we're getting there. So I take my power supply off, I switch it up to my ohm meter, and put it across. If everything is working right, and we take some of those outside factors out, we should get 5.9 ohms. 3.5, 3.4. Okay, so it's not perfect. We're off by 2 ohms there. It's not perfect, but you're going to have to trust me that this absolutely does work using Ohm's law to calculate these numbers. Okay, so when we're working to find resistance total, we need to have voltage total and current total to be able to do that. When we're trying to find resistance of a certain part of our circuit here, where we have 4 lights here, if we want to find the resistance of L1, we need to know what the voltage drop of L1 is and the current of L1 to be able to figure out the resistance of L1. And the works in reverse as well. If we have 3 of Ohm's law, if we have any of these 3, if we know what the resistance total is and the current total is, we should be able to figure out the voltage total. So whichever one you're looking for, if I'm looking for current, I hold my finger over it. If I know what the resistance of L1 is, and I know what the voltage drop across L1 is, I can figure out what the current of L1 is. Okay? I'm going to give us some problems. I'm going to give you guys 2 problems this week to do. Just send me back the answers, and we'll go from there.